everybody. Mr. Copy here, and this video is on something called logistic curves or logistic growth. And this is actually super interesting, I'm serious, because the idea here is exponential growth is cool and all, and some stuff grows exponentially, but in the real world, stuff doesn't grow exponentially forever. You know what I mean? Like stuff doesn't keep growing and growing and growing. Eventually, it kind of levels off, at least for most things. So if you think about populations, or really it's honestly it's most things, they don't increase exponentially. They level out at some point because of real world factors that are limiting them becoming unlimited, right? So there's not going to be an unlimited amount of bacteria, you know what I mean, or something like that. Or the population of a city isn't going to reach infinity. That doesn't make any sense. There's going to be some maximum amount. And depending on what you're talking about, if you're talking about a population, they might call that the maximum population, or if you're talking about other situations, they call that the carrying capacity. Okay? And before I talk about this, what this type of curve looks like is like this. I'll show you. It starts out looking like it is going to be exponential, and it does behave exponentially. It's like, oh, it's going up and up and up and up and up, but at some point it kind of levels off. And what happens when it levels off? It starts to approach some bad drawing, Mr. Cuddy. Starts to approach some horizontal asymptote, and we call that the carrying capacity. You usually call it L, the limiting factor, or the carrying capacity. Okay, so there's a lot of things in the real world that follow this type of a pattern. This is called logistic growth. Okay, there's kind of an important point right here. What happens right here? Well, this whole function's increasing. This function's increasing from negative infinity to infinity, but at that blue point, the rate at which it is increasing begins to decrease. In other words, that is a point of inflection. And the cool thing to kind of note is that occurs at half of the carrying capacity. So once you reach half the carrying capacity, the rate of growth begins to slow. It is still going up, but it's going up at a slower speed. Cool. This is logistic growth. Logistic growth is really common in sciences. You'll see it a lot in college. What we want to talk about today is, first off, we think about logistic growth as being the solution to a certain differential equation. Okay? And it's where the growth rate is proportional to the amount present and the fraction of the carrying capacity that remains. You don't really know that. If you encounter a logistic growth, or excuse me, a differential equation that looks like this, or if you have everything in terms of y, then dy dt would be k times y times 1 minus y over L, then the solution to this differential equation is a logistic growth function. Okay? We do need to talk about a couple of the variables here. Here, L is the carrying capacity. We mentioned that. So obviously that's going to impact the situation. And there's also a constant K that you that changes based on that model. Okay. Cool. So if you encounter this type of differential equation, its solution is a logistic function. Stick with me here. This is where it's going to get a little intense. So here's the differential equation you're going to come across. K is going to be a number, just a random constant, or it's going to be a constant for the problem. L is going to be the carrying capacity. And the solution to this differential equation is this function. This function is the logistic function. This function is going to give you a curve that looks like this. Okay? So if you graph this, it looks like this. Okay? Now this is this, oh sorry, by the way, this K is the same as this K, this L is the same as this L, and this B is a new constant. Okay? Now, if this is the solution to this differential equation, well, then we should be able to take the derivative of this and get this, right? That's what, if this is a solution to this, or if this is a solution to this, then the derivative of this should follow this pattern. Let's do the derivative of this and see that it looks like this. Okay, this is kind of a deriving the formula thing. So stick with me here really quick. I'll do it quick. First, I'm going to do the derivative of this. I'm going to do quotient rule. Okay. So when I do the derivative of this with respect to time, I do quotient rule, low d high less I d low over denominator squared for show. The top is just a constant, so d high cancels that out, and I'm left with this. Okay? Again, I'm trying to show that the derivative of this is this, and that is why this is a solution to this differential equation. I'm going to simplify this in a very specific way. How? Those two negatives cancel. I'm going to pull the k out, it's just a constant. And I'm going to split up this 1 plus be to the negative kt squared. And I'm going to split up the L and the BE to the negative KT. Why? Because I want this to simplify a certain way. The L over 1 plus BE to the negative KT, oh, that's just Y. That's just Y. So I'm going to replace, so I'm going to have, whoops, dy dt equals K times Y. Okay, it's starting to look like this. Now for this part, I need to be a little bit careful here. I'm going to do some fancy math. Stick with me. Not fancy, just algebra. If y equals L divided by 1 plus BE to the negative KT, then I can say y, I'm going to put this in a little bubble. I can say y times that equals L. It's going to a little rearranging. I can rearrange that and say, oops, sorry. L over y equals 1 plus BE to the negative k. What it's going to let me do is replace this 1 plus BE to the negative kt with an L over y. And then the BE to the negative kt, well, that's just going to be L over y minus 1. Again, why am I doing this simplifying? Because I'm really trying to get it to look like this. Okay. Okay, and now I'm almost there. What else? Excuse me. What other simplifying can I do here? Give me a second. I can do some rubber banding here. Yeah. So a little butterfly. I get 1 minus, what's 1 divided by L minus y, multiplied by the reciprocal, it's y over L. And I did it! The derivative of that original function y is this, which is what it's supposed to be because it's the solution to the differential equation. Okay? Let me say something really important here. If you came across this differential equation, you need to know that this is the solution to it. Because otherwise, how are you going to solve the differential equation? You're going to try and separate the variables. And I'm going to tell you right now, trying to separate the variables on this is either impossible or extremely hard. Okay? You don't want to have to try and solve this by separating the variables. You want to know that the solution to this differential equation looks like this. This needs to be a fact that you have memorized. You see a differential equation that looks like this, you do not separate the variables. You do not do what we've been doing. You recognize that the solution is going to be logistic. You have to know that. Okay? Well, I'm going to run through 2 examples with you guys. Okay? Remember, these functions we're talking about look like this, and this is going to be really helpful. Okay. First, there's a bunch of typos in the answer keys, just so you know. So, note some typos in the answer key. We're going to run through 2 examples together here. So, it says 10 grizzly bears were introduced to a national park 10 years ago. Today, there are 23 bears. Max park can support is 100. Assuming a logistic growth model, when will the bear population reach 50, 75, and 100 bears? Okay, so it's following this logistic growth pattern. Cool. Okay. I'm going to kind of just walk through this with you guys. Okay. So because it's logistic, it's going to be a solution to a differential equation that looks like this. Okay. Its equation is going to look like this. Well, what do I know about this situation? Well, I know that the maximum amount of bears, that carrying capacity, that L, is 100. They just straight up tell me that. Okay. What I don't know, if I'm trying to write this equation, because I want to know this equation if I'm going to predict when it's at certain y values, which is what they're asking. I need to figure out the b and the k. These are two different constants that I need to figure out. Okay. Luckily, they tell me 2 points. They tell me there were initially 10 bears. At time 0, the population was 10. And they tell me currently there's 23 bears. At time 10, because it was 10 years ago that they put in the bears, at time 10, there's 23 bears. These 2 points I'm going to stick in to solve for these 2 missing constants. Okay. Which point should I stick in first? If you stick in the point that's associated with time equals 0, it's going to be easier. Okay? Because that's going to be easy. If you stick in 10 for the population and 0 for the time, you get this equation. Easy. The k just went away. It was just a linear equation, and we solved for b equals 9. Okay. Now my logistic model for this bear population looks like this. What do I not know? I still don't know the k, but that's okay, because I still have another point that I can plug in. Okay. So I'm going to grab that other point. When time is 10, the population is 23, and I'm going to algebraically solve this equation. You guys know how to solve this equation. I'm going to cross multiply and then divide the 23 over. I'm going to get this type of an equation. It's an exponential equation. We just did this in pre-calc accelerator. I'm going to subtract 1. I'm going to divide by 9. I'm going to do the natural log of both sides. I'm going to flip it into logarithmic form. I'm going to divide by -10, and I'm going to get my k. Here is my logistic growth function that's going to match the initial conditions they give me. You could, of course, check this. When I plug in 0 for t, I should get out 10 bears. When I plug in 10 for t, I should get out 23 bears. If I plug in a giant number for t, its carrying capacity is 100, so this population of bears should approach 100 but never hit 100. Okay. Let's actually answer the question now that we have our function. How are we going to figure out when this equals different y values? Well, you can solve it on your calculator. So when is it going to equal 50 bears? You could use second calc intercept and figure out that's going to happen after 22 years. When's it going to have 75 bears after 33 years? When's it going to have 100 bears? The real answer to this is never, right? It's never going to reach your carrying capacity because we have a horizontal aspect there. But it gets closer and closer, okay? As time goes on. Cool. Okay. I'm going to look at a slightly different problem with you guys now. Okay. The carrying capacity for frogs is 3,000. Sweet. They're just telling me the L right away. The growth is proportional to population N and 3,000 minus N. Last year there were 500 frogs. This year there's 1,000 frogs. How long will it take for the population to reach 2,500 frogs? Okay. I want you to note that they don't tell me to use a logistic growth model here. They kind of hide it. And they say the growth, the derivative, is proportional to N and 3,000 minus N. When you see that, you should think this. I'm going to call my population P. The rate of change, the growth of the population, is proportional. I got to put a constant there, proportional to N and 3,000 minus N. Okay. we need to do something really important here, which is this doesn't quite look like our logistic growth differential equation. Why? Because that has a 1 minus here. Yeah, you know what I'm talking about? And that's okay. It really isn't a big deal. We can fix that. Okay. Sorry, I was doing something silly. My bad. Miss Lemke's gonna get all mad at me. No, I'm just kidding. They called the population n. So we need to call it n. So dn dt is k times n times 3000 minus n. What I'm doing here is I'm making sure that I have a constant of 1 here while I'm GCFing out 3000. So I'm going to get this model. Okay? And then this is 3000 times k. I can just call this. Sorry, why did I put an L there? That should be a 3000. My bad. I have a 3000 times k here. I can just call this k. That's totally fine. It's just a constant. 3000 times a constant is just a constant. Okay? Just change what the constant is. I can call it k prime here, and now it's k. Okay. So this is fitting a differential equation whose solution is logistic growth. I will say that again. They are describing this differential equation. This differential equation should be setting off alarm bells in your head. Oh, this is ky times 1 minus y over L, where L is 3000. This is a differential equation whose solution is logistic. Can't say that again. So I can't say that enough. Okay? You should immediately look at that and be thinking about a solution to that differential equation that is logistic. So the solution to that looks like this. Okay. We are not going to separate the variables and do the antiderivative. You need to just have this fact in your head. Okay. Now I know L is 3000. They told me the carrying capacity. They're asking me how long will it take for the population to reach 2500. I need to solve this differential equation. Okay, I have the solution here. I just don't know what the b is, and I don't know what the negative k is, or the k is. Okay. Luckily, again, they tell me some points that I can plug in, some algebra I can do. Last year, there were 500 frogs. Let's just start time last year. So let's say at t equals 0, there's 500 frogs. This year, okay, well then that would be time equals 1, there's 1,000 frogs. Okay. We're going to plug these points in to solve for b and k. Which one should we plug in first? We should plug in the one with time equals 0 first. Why? It's going to make the k go away. Okay, so if you plug in the time equals 0 one, we get b e to the 0. Well, that's just b. 1 plus b, 3000 over 1 plus b equals 500. Solve for b. Check, check, check. Now we're almost have our solution. We got 3000 divided by 1 plus 5 e to the negative k. Ooh, I got to figure out that k. How am I going to do that? I'm going to plug in the other point. Time is 1, and it's 1000. This is algebra we should be able to do. Going to trust that you remember your ATH, MH. I'm going to solve this equation for k, and I'm going to get that k is 0.916. Now that I have my k and I found out my b, I have the solution to this differential equation. Ta-da! This is a logistic growth function. It is the solution to this differential equation. Cool. And it models this population. So then when they're asking me a question, whatever question they ask me, it should be pretty easy to answer. They could ask me to plug in a time, they could ask me to plug in a population, I can do either one. They're asking me when will the population reach 2500? I can solve this algebraically, or if I have my calculator, I can totally just solve this on my calculator. Typing in the y1 and y2 and figure out where they intersect, and it gives you out that happens at time 3.514. And let's remember that we're already at time 1, so that's 2.514 years from now. Cool. Check. Okay, one more problem here we're going to do together. And again, this is just slightly different. So it says a colony of bacteria has a population limit or carrying capacity of 18,000. At time 0, there were 1,000. The growth is modeled by this. Find a formula for the number of bacteria. Okay. You need to look at this differential equation and think, this looks logistic. This looks logistic. Note that the logistic thing has to be factored. Okay, it has to be factored, and there's a ky. You just need to be able to write this down off the top of your head. This is the differential equation that gives logistic growth. Okay, this looks like this. I need to do some algebraic manipulation. Please note that this is factored. That's what I was saying. This is factored, so if you come to a differential equation that you think might be logistic, but it's not factored, make sure you factor it. This doesn't quite look like this because of the 18,000, so I need to GCF out the 18,000. Grab out my good old-fashioned TI-83. I'm going to rewrite this like this. 5.4 y times 1 minus y over 18,000. I GCF'd out an 18,000. And now this differential equation looks exactly like this. Right? What's L? 18,000. What's K? 5.4. So now I can just write the solution. That's one little caveat there. But I can just write the solution right after that. L divided by 1 plus, I got that B. Okay, so when you go to try and write your solution, there is one more variable. Why is there one more variable to the solution of this differential equation than in the derivative? It's the plus C thing. So it's kind of hard to see, but whenever you do an antiderivative, you have a plus C, you have an extra variable that you don't know. Here the plus C ends up being like stuck in there as multiplication, but it's the same idea. Okay, so you need some more information to actually nail down formula, and luckily they give you that extra information. They say at time 0, the population was 1,000. So I need to solve for that B. I'm going to plug in 1,000 for the population. I'm going to plug in 0 for time. That's going to cause it to be e to the 0, which is just 1. Boom. B is 17. I have my model. Check. Cool. That is a function that models that bacteria growth, and it's a solution to this differential equation. Cool. We're going to pause there. This is definitely something that you need to memorize. Going all the way back to the beginning, you need to be able to look at this differential equation and tell that the solution looks like this. All right. That concludes this video. Thanks for watching, guys.